Hello, everyone. Thank you so much for joining us today on our live session. This is Matthew. I'm one of the instructors for the online class that we offer through Coursera and through Udemy. So if you're joining us through that, welcome. I help run all of the online components. I'm going to hand this over to Professor Impey, and he will say hello, and we'll get right into questions.
Welcome everyone to another online Q&A session for the astronomy courses, and there's close to 200 of you live again today. Very good, great number. So let's get started.
Excellent. Thank you very much. The first question is from Slingshot, who's on with us live. If the dark energy is increasing, then shouldn't some of this energy being converted into mass or matter? Like, how does, what's the connection between mass and energy? But then also it seems like there's this dark energy, dark matter relationship. Is there any connection there?
The dark energy as a component of the universe is not technically increasing as an energy component of the universe. It's constant. In fact, it's constant in direction and in cosmic time, as far as we can tell, which means it behaves very much like Einstein's cosmological constant from 100 years ago. What's increasing about the dark energy is its effect on space-time, because pretty much the only thing we know for sure about dark energy, whatever it might be, is that it's causing space-time to expand at an accelerating rate. So that's what's increasing about dark energy. The actual amount of it is not changing. The relationship between dark matter and dark energy is unknown. As components of the universe, dark energy exceeds dark matter in its mass energy equivalence by a factor of 3. And since dark matter would cause the universe to decelerate or slow down, and dark energy causes it to accelerate, the dominance of dark energy is why the universe is expanding at a faster and faster rate. And since as the universe gets bigger, the density of dark matter and normal matter dilutes or thins out, and its gravitational effect diminishes, this is the future of the universe, to be governed by dark energy. And in the far future of the universe, dark energy will dominate vastly the energy of the universe. And in that sense, it's increasing. It's increasing in its relative contribution relative to dark matter.
Thank you very much. The next question is from Wolf and Bree, who's on with us live. Why did we expect the detection of gravitational waves would help answer questions about the multidimensional theories? And also, what did we actually learn from the detection of gravitational waves?
It wasn't clear whether the anticipation of gravitational waves was going to illuminate our theory of gravity. So the question's referring to multidimensional theories, which are fundamentally string theories that go beyond current gravity theory to have a sort of unified theory of the forces of nature. Gravitational waves are a prediction out of general relativity, and their observation is an affirmation or confirmation of general relativity. So in that sense, they do not illuminate these more profound issues of unified theories of nature. However, there is a possibility that they might, because in addition to the gravity wave signatures from merging black holes that we've seen and merging neutron stars that we've seen, there are gravity wave signatures that are anticipated from the very early universe. These are not signatures or signals that we can detect with LIGO or any current interferometer, but they are possibly signals that might be detected in the future. And out of the very early universe, the gravitational wave signals or signatures could possibly speak to these unifying of the forces of nature and string theory and the multiverse and all these more exotic concepts. So that's a prospect. I would say it's a fairly distant prospect, because it would need substantial innovations in our ability to detect gravity waves.
Excellent. The next question is from a few different people. They have several people on would like to know how to get started in astronomy, and there are people who are interested in it sort of professionally and also as a hobby. So what are your suggestions for both of those areas? How did somebody get into the field of astronomy participating?
Right. So I'll deal with the professional and the recreational versions of this question. To be a professional astronomer, almost everyone starts by studying physics. So the route into the gateway drug, if you like, to astronomy is physics. And that's what I did as an undergraduate, and that's what most of my colleagues did as undergraduates. So you need a bachelor's degree in physics or physics and astronomy, or possibly mathematics, and just occasionally a more distant related field in engineering or even life science. But there's a pretty standard path because astrophysics is the study of the physics of the universe, and so you need physics to applying out into the universe. So there's a lot of physics. And for example, at my university, if you're doing an undergraduate degree in astronomy as an astronomy major, you're taking 70% of the credits that a physics major would take. So most of our students do the double major. So there's a huge overlap between what you study in the curriculum for which we would call astronomy and what we would call physics. So that's the pathway. And then the advanced degree, the astronomy degree, master's or PhD, that can, of course, focus more specifically on astronomy or astrophysics. So that's the path for a professional astronomer. For a recreational astronomer, it's much easier. There's a lot of adult distance learning options, including the 3 courses that we run, 2 on astronomy and 1 on astrobiology, 2 for Coursera, 1 for Udemy. And there are other similar astronomy courses, and many of these are free. So you can get a pretty good base coat of paint of astronomy knowledge, perhaps not at the technical level with full mathematics and the full rigor of a 4-credit class, but you can learn a lot from online courses. There are books, of course, many books, too many for me to start listing them now, that'll help ease you through the field. And for hands-on experience and to join a community of recreational astronomers, that's also pretty easy because almost every community of any size across the country and throughout Europe and the world has amateur astronomers that form clubs. And if you just sort of Google amateur astronomy and with your location, you'll very likely be able to find a club nearby. NASA has a website called the Night Sky Network, and that's astronomy clubs that affiliate with NASA to get free educational materials. That's a pretty good resource. They list something like 600 clubs in the US. So, and these clubs are happy to have new members. They're usually very active. They have star parties. They have information sessions. Sometimes they have guest lectures if there's a university or astronomers professionally working nearby. So just find where your local club is, and that'll be a great way to get started.
Thank you very much. The next question is from Ayush, who's on with us live. How is the atmospheric blanket created around a planet or a terrestrial planet in particular? And why do only some planets have atmospheres and others don't? What's the criteria?
Right. Planetary atmospheres is a complicated topic in planetary science. So the planetary science department across the street from where I work, there are several courses, undergrad and grad courses, of just about planetary atmospheres. So it's a complicated subject, but the general principles are fairly clear. The ability of a planet to hold an atmosphere essentially depends on its gravity. And so very small planets cannot hold an atmosphere. The example in the solar system is Mercury, which essentially has no atmosphere. Our moon is similar size to Mercury, and it's not a planet, but it also has no atmosphere. Whereas large moons and planets that are terrestrial planets can have atmospheres. Titan, for example, is a moon in our solar system that's massive enough to hold an atmosphere. And then we have the Earth and Venus. Mars, being a small planet, fits this sort of correlation because it has a rather feeble atmosphere. In the formation of planets, the atmospheres are typically created by outgassing. So the planets start molten, the rock is molten before it solidifies, and if it's a big planet, it'll have tectonic or magma activity. And that activity is what releases gas into the atmosphere. And so, for example, on the Earth, the nitrogen came from outgassing. There was also carbon dioxide from outgassing and from volcanism early on. The oxygen is unusual because it was created by microbes, by oxygen metabolizing microbes billions of years ago. But a planet with a carbon dioxide atmosphere like Venus or Mars is typically created by geological effects. Also, light gases are released early in a planet's history. Hydrogen and helium, the dominant gases in the solar system and the sun when it formed. But those gases are light, and so they tend to leak out into space for a given planet size quicker than others. So the planet is able to hold the more massive or larger molecules more easily than the lighter molecules. So hydrogen and helium escape, whereas heavy molecules like oxygen and carbon dioxide and nitrogen are retained. So these are general principles that sort of tell you what kind of gas you might expect to see in a planet atmosphere. And planet atmospheres do evolve over time. So we have good evidence that Mars had a thicker atmosphere in the distant past, but its weak gravity was unable to retain it over time. So it's now very thin carbon dioxide atmosphere, whereas Venus and the Earth, very similar in mass, have held thick atmospheres for billions of years.
Thank you very much. The next question is from Narun Joe, who would like to know, can dark matter patches exist isolated in space? And can they form things like dark matter stars or dark matter galaxies that can be distinguished from normal ones?
Yeah, it's a good question. Dark matter is the dominant mass component of the universe. It only obeys the force of gravity. It does not interact with radiation or light. It does not emit light or absorb light. So it really only is following gravity. And as the universe has evolved, dark matter, acting on itself as the dominant mass of the universe, has clumped and clustered. And the things we see as visible galaxies are essentially pools of baryonic material, normal protons, electrons, and neutrons that are luminous because they collapse, that material collapses to form stars, at the center of large halos of dark matter. So the baryonic material, the normal stuff that we're made of, is able to collapse and lose and radiate energy, and so form small collapsed objects like stars at the center of a much more diffuse sphere, if you like, for a galaxy of dark matter. The dark matter does clump, and there are some indications that when the dark matter halos, as they are called, are small or weak, they might have very few baryons attached. And so there's been a constant research initiative to try and find dark galaxies, which is to say galaxy-sized dark matter halos that don't have any visible counterpart or set of stars attached to them. And there are a few examples that have been found. Sometimes that's just because the stars that form are weak and feeble and diffuse, spread out, so that it's very hard to see with a telescope. And occasionally we see signs that a dark matter halo has formed a small galaxy with a burst of star formation early on, billions of years ago, where the supernovae from that star formation blew out the remaining gas, and essentially you have a dark matter halo where the normal material has dissipated or left. So yes, it is possible to have dark galaxies or dark matter halos without visible counterparts, but the dark matter acting only by gravity and only slowly over cosmic time is never able to form extremely dense objects. So there is no sign nor expectation that dark matter will form stars or star-like objects. Of course, it can't make a star because dark matter cannot shine or emit radiation, but it can't even really exert enough gravity on itself to collapse into a dense type object like a star. So that you can have dark galaxies, galaxies made pretty much purely of dark matter, but not dark stars.
Excellent. Thank you very much. The next question is from Lin Chen, who would like to know, how do scientists detect and make sure, or how are they sure of what is the material of the Earth's core? Is it possible there's some empty space or area inside the core? How do we know what we know about the center of the Earth?
Right. That's a good question because, as most people know, the deepest holes we've dug into the Earth are extremely shallow. If you analogize the Earth to an apple, then the deepest holes we've dug, there's one in Russia that I think is the deepest shaft ever dug into the Earth's crust, is not as far as the thickness of the skin of that apple. So we've really only directly explored the crust of the Earth, not even into the mantle. So between the crust and the mantle and interior to that, we are fairly confident there's a solid core and then a liquid core beyond that. And these are mostly made of the heavy metals that sunk to the Earth's center when the Earth was molten, so iron and nickel. So how do we know that that's the structure of the Earth, that it has a solid spinning core and a liquid metal core outside that, and then the mantle of mostly rocky material and the lighter crust beyond that? We know essentially because of seismic waves. So we can follow sound waves through the Earth, and with various extremely sensitive detectors for seismic waves, and also mechanisms for essentially pounding on the Earth and generating a seismic wave on one place and then looking for how it passes through the Earth. These waves will travel at different speeds through different densities of material, and they will refract just like light waves refract through different densities. And so by looking at the arrival times and the deflections of seismic waves passed through the Earth in various directions, we can map out the density profile of the interior of the Earth. So it is actually quite a mature science to map out the interior density of the Earth all the way through to the center by this method. And these densities very clearly distinguish between iron and nickel, heavy elements and metals, and lighter rock that's mostly silicon and carbon and oxygen in various combinations. So we don't know the exact chemical composition of all these regions, but we know their crude chemical composition. We know their sizes. We know from just the physics of what happens to rock when it's compressed with a certain amount of gravity, what the state of the rock would be and whether it can be liquid or must be solid. We know the Earth, of course, has a magnetic field, and that magnetic field is tethered into the core. And so the persistence and the strength of the Earth's magnetic field is yet another indication of what the interior of the Earth is made of. So by this fairly sophisticated subject now that's been going for half a century of mapping seismic waves, we really do know what the interior of the Earth is like.
All right, the next question is from Sarah, who's on with us live. Why does matter under low pressure produce an emission spectrum, but produce continuum blackbody radiation under conditions of high pressure? Basically, when does the transition from emission to continuous spectrum happen, and how does that work?
So for spectra, the two parts of the conditions that are relevant are the temperature and the pressure or the density. So the emission spectrum is coming typically from a hot gas or a plasma, where the density is low but the temperature is high. And that temperature is high, and so it is forcing the electrons to change their positions. They're losing and gaining energy according to quantum rules. And those amounts of gain and loss of energy correspond to a fixed set of spectral lines for each element. So when we look at an astrophysical gas or a plasma at temperatures of 5, 10, 15,000 Kelvin, which is typical of gas that might be near a star like a nebula or something like that, or the outer atmosphere of a star, you're going to expect to see these emission lines as the gas is excited and the electron states change according to quantum rules, making the sharp set of lines in the spectrum. Any gas or any material that has a temperature will also have a thermal spectrum associated with, or blackbody spectrum associated with that temperature. So even a plasma that might have a temperature of, say, 15,000 Kelvin will emit blackbody radiation with that temperature. But if it's a very diffuse or low density plasma, the intensity of that radiation is quite modest. Whereas if you have a much denser object like a solid or a liquid at a particular temperature, then the blackbody radiation will be much stronger. So the relative strength of the thermal or blackbody radiation depends on the sort of density of the material and its internal pressure.
The next question is from Stardust Sagittarius. Can you please explain your views on the so-called mysterious Planet X?
Planet X, yes, that's a good perennial question, issue of astronomers that I've been thinking about for decades, actually. It's the general issue is, do we really understand the population of planets in the solar system? Is it possible, for example, that there are close planets to the sun that remain undiscovered, and also are there planets farther out that we haven't yet discovered? The answer to the first question is no, and the second question probably yes. Planet 9, Planet X, or sometimes called Nemesis, that's an idea that includes the idea that there might be a planet that on the far side of the sun from the Earth, and so it's essentially shielded by the sun from our view, so it sort of orbits with our orbital frequency, but just by almost a conspiracy of physics is hidden from us. That is a very easy hypothesis to rule out because the effect of an interior planet on the orbit of Mercury, the innermost planet that we do study, would be very dramatic, would be very clear. So basically, our modeling of Mercury's orbit is only really being caused by the sun, down to very fine detail, is sufficient to completely rule out any substantial planet close to the sun. Say so close to the sun that we might have trouble observing it. It simply couldn't be there at anything like even a fraction of Mercury's mass. Planet X, further out in the solar system, a sort of outermost planet that might dwarf, say, Pluto in size by a factor of a few, that's possible. That planet might, because of perturbations in its orbit, be far from the ecliptic, so it may have an orbital tilt relative to the plane of the solar system. And that means the region of sky you'd have to search to be sure of finding it or ruling it out is pretty large. And those surveys have been underway for a while, but they're hard because these exterior planets that are going to be beyond, say, 40 astronomical units into the Kuiper belt out to 80 astronomical units, those get so little of our sun's light reflected back to us that they're extremely faint. And if they're small and faint, they're going to be hard to see, even though they move relative to the star patterns when you take a deep image. Within a few years, those surveys will be complete, and we'll know what the number of outer planets in the solar system that rival Pluto in mass are. And there are a couple that have been found already. But that survey will be complete. But there's no room in the solar system, either inner or outer, for any large undiscovered planet.
All right, the next question is from Laurentio, who is on with us live. A recent study implies that the universe is not isotropic, but is actually lopsided or anisotropic. What's your take on this, and what would this imply about the universe itself?
So isotropy is a really important part of cosmology. It's essentially an assumption, which is that the universe, it's a part of the Copernican principle that we don't live in a special place in the universe. There's nothing privileged about our position or location, either in time or space. And a corollary of that Copernican principle is isotropy, that the universe will look on average the same in every direction we look, which is to say, if we count galaxies or look at large regions or volumes of space in different directions, we shouldn't see any gross differences from one side of the sky to the other. And that's generally held to be true. But every now and then, including recently from an X-ray survey of clusters that is the subject of the question, there's hints that the universe may not be exactly the same in every direction. And so there is anisotropy at a level beyond what would be expected in standard cosmology. Now, obviously, the universe does have variations in density. There are clusters and superclusters and voids and so on. But the point of the isotropy is that when you average over hundreds of millions of light years of distance or volume, you should see about the same thing everywhere you look. And this one study implied that that might not be the case. I would say there's an asterisk attached to that interpretation because the objects being studied with X-rays and the hot gas associated with these clusters is not fully understood physically, and there's some assumptions that are made in interpreting the observations. So most astronomers are declaring this a tantalizing result, not a definitive result. And isotropy is such a core assumption of cosmology, and it's been so much affirmed by other observations, that the bar is set pretty high for proving anisotropy. And this recent study so far does not clear that bar. I think you're muted, Matthew.
Oh, I'm sorry about that. The next question is from Percival Lowell, who is on with us live, which is strange since he's been dead for many years. He or she and their son Cinna would like to know what's the status of the James Webb Space Telescope, and what do we expect to learn from it, and what kinds of testing are they doing on the Earth before they send them into space?
So the James Webb Space Telescope is moving forward. It's had some delays. It's obviously been hugely delayed from its original plan. I think relative to its very original plan, it's slipped by a decade, and its price has ballooned from a couple of billion up to probably $10 billion by the time of launch. Currently, launch is planned for late 2021, I think October 2021, but it may actually be slipping because under the coronavirus lockdown, NASA is unable to do some of its final set of tests prior to integrating the telescope into the spacecraft. And so the launch schedule is essentially slipping by 1 day per day and has been for the last couple of months. So James Webb may slip into 2022 or whatever. Now, there's not a particular launch window for James Webb, as opposed to a planetary mission like a Mars mission where you have to wait for the closest approach, and that happens about every 20 months. So the Webb can slip by a few months and it won't be a disaster. It's just been a long wait. There have been some problems that people have read about in some of the tests. There was a shake test that actually dislodged part of the solar panels when they were being given an extreme shake test. So for the launch of these telescopes in powerful rockets, you have to test the components to a margin that exceeds the g-forces they're expected to experience. So for this kind of a launch, g-forces should only be about 8 or 9 g, but they will shake test or do violent testing of components to about 20 g to give a real margin. And some of the components actually failed the most recent test like that. So they're going back to re-engineer them. The instruments have been tested separately on their own without being integrated into the telescope assembly. And those instruments, a couple of them have had also issues with their detectors, but those have been resolved. And in fact, the launch delay in the last couple of years has actually helped the instruments get ready for prime time. So the instruments are all ready to go. The telescope has had some little bumps along the way in its various components and systems, but those seem to be resolved too. And so it's now just a waiting game. And it's expensive because there's what NASA would call a marching army of engineers and technicians that are required to get a complex mission like this off the Earth. And you have to keep employing those engineers, to keep monitoring and making sure all the systems are fine. And as the launch is delayed, the cost of the mission just keeps going up and up. And it's already reaching a level where Congress has essentially said no more. We're not going to give it any extra money. So you need to launch it with the budget you have. And NASA is doing their very best to make that happen.
Excellent, thank you. The next question is from David, who's on with us live. Black holes are often depicted as frightening and dangerous, consuming everything in their path. But are they really any more dangerous than a star of the same mass?
No, good question, and they're not. So if the sun mysteriously overnight was squashed by some evil alien empire into a black hole, which would mean if you crushed the sun down to about 3 kilometers, it would be a black hole. If that were to happen, of course, life on Earth would eventually die because the sun's radiation would disappear, but the Earth would continue in its orbit uninterrupted. So at the distance of the Earth from the sun, or even Mercury or any of the planets from the sun, if the sun were a black hole, it really wouldn't change anything at all. And so that's the sort of general misunderstanding about black holes. Yes, they are sort of rifts or clefts in space-time, a piece of space-time completely pinched off. But remember, that's a very small region. A star black hole is only the size of a small town or city, so a few kilometers across. And then the extreme effects of general relativity are perhaps felt for maybe 100 Schwarzschild radius. Schwarzschild radius is the formal name given to the radius of a black hole. So maybe for a factor of 100 beyond that, to distances of hundreds or maybe 1,000 kilometers, you have extreme space-time distortions, bending of light, slowing of time, etc. But that's still very small distance compared to the size of a solar system. So the distortions of general relativity, the extreme effects on space-time, are really only true proximate to the black hole. And for the same reason, black holes are not cosmic vacuum cleaners sucking up everything in their path or around them. They, again, only have the same gravity that a star of their mass would have at a large distance from them. And so they're not going to consume matter any more voraciously than a star of the same mass would at a large distance.
Excellent, thank you. The next question, there's actually been a few people have asked questions related to this, so I'm gonna, kind of combine them all together. Do you believe in aliens? What are your views on aliens? Do aliens exist? What are the chances of there being aliens? And then finally, could something like the coronavirus be an alien virus from somewhere else?
Okay, well, I'll treat these as two different questions. Do I believe in aliens? My personal belief? Well, I was a fan of the X-Files, a show that many people are familiar with, ran for a number of seasons. There were movies from it. And as you remember, there were agents Scully and Mulder was the sort of credible one, and he had a poster in his basement office which said, "I want to believe," and he did believe in aliens and UFOs and so on. And Scully, the female agent, played by Gillian Anderson, was a non-believer. She was the scientist and the skeptic and so on. So I'm sort of more of the Scully role rather than the Mulder role here. I don't think it's implausible that intelligent civilizations may exist in the universe, even within the Milky Way. But I don't think we've had any kind of convincing evidence that they have visited the Earth or that they do actually exist. I think they could exist, but proof is something that you need a pretty high bar for. As Carl Sagan said, extraordinary claims require extraordinary evidence. So postulating the existence of intelligent aliens, especially by visitations to the Earth, is setting a very high bar for evidence. That bar simply hasn't been met. Scientists don't reject out of hand the possibility, but they ask for the evidence, and evidence so far has been lacking. And remember, photographic evidence these days with Photoshop and digital manipulation is really not a good form of evidence, and eyewitness reports are even not very reliable, as anyone who's read the histories and chronologies of jury trials and their frailty would understand. So I don't think they visited. I don't believe in UFOs as they're presented, but I think aliens could exist. For the coronavirus, that's an interesting question. If you want to imagine that alien civilizations exist and that they visit the Earth and might have a malign intent, then yes, they might indeed want to wipe us out and sow seeds of destruction, presumably with technology at their disposal. Genetically manipulating a virus to turn into a pathogen would not be a difficult thing. We can do it ourselves pretty much now. But I think there's no reason to reach for that hypothesis with coronavirus. There's, again, still no general evidence that alien civilizations do exist or visit the Earth. And we have a perfectly reasonable natural explanation for the coronavirus. There's obviously a debate playing out in the media right now over the exact nature of how the coronavirus started, but the general biological and epidemiological opinion is that it is a zoonotic virus, which is to say it's a virus that passed from animal species to humans and is part of a family of coronaviruses, of which we're familiar with dozens of other examples. So it's a very familiar class of viruses, and others of which have crossed the species barrier from animals to humans. So it's part of a pattern of viruses that we're very familiar with, and it has entirely natural causes. Unfortunate, but natural.
Excellent. The next question is from one of our live viewers. Can you please explain what an electromagnetic wave is? Why do electromagnetic waves move? How do they form? How do electromagnetic waves work?
So the theory of electromagnetic waves is a beautiful piece of physics that comes from compatriot of mine. I'm a Scotsman, and James Clerk Maxwell was a Scotsman working in the middle of the 19th century. And so Maxwell came up with a set of equations, 4 equations that describe varying electric and magnetic fields. So the history of the subject was that through the 18th century and even back into the 17th century, people did various experiments with electric fields and magnetic fields, static electric and magnetic fields, like when you had a charged object with static electricity, or you had a bar magnet or a static magnetic field. And by the time of Faraday, they started to notice that if you changed an electric or a magnetic field, these things were coupled. So you could change a magnetic field and generate an electric field, and you could do the opposite. Well, that's very interesting. So people realized that electricity and magnetism were related to each other in a very interesting and profound way, and that was the insight of Faraday in various experiments. Also around this time, it was possible to start generating electromagnetic waves, and typically these were radio waves. So when you either oscillate or vary a magnetic field or an electrical field, you can create electromagnetic waves. So these phenomena were observed in the lab in various situations, but the theory, the underlying theory of them, which really told us how they worked and explained them physically, came from James Clerk Maxwell in around the 1860s. And he unified all these phenomena of electricity and magnetism into a set of 4 equations that describe varying electric and magnetic fields and how they can generate waves that travel through space, through a vacuum, or through a medium like air at the speed of light, 300,000 kilometers per second. So the speed of light is a constant that emerges in the theory of electromagnetic waves by Maxwell. And so with this theory, we fully understand the phenomena, and we realize that light is just one example of a family of electromagnetic waves all traveling at the speed of light, where the variable is wavelength or frequency. So we've had this theory now for about 150 years. It's one of the profound building cornerstones, if you like, of physics that hasn't really changed in 150 years. It's still a cornerstone of physics, and students that take physics classes for a degree still learn basic electromagnetism the way they might have done 100 years ago.
Excellent. The next question is from Anvashak, who sent an email, and I believe it was on with us live. According to the Big Bang theory, the universe went from being opaque to transparent very quickly. Shouldn't it have become transparent more gradually?
There is a time that it takes to go transparent. The chronology is that the universe initially is very hot. It's a plasma. So even though there are electrons and protons and neutrons, the electrons are not attached to the protons and neutrons, so they're not stable atoms. And in that situation of a very high temperature and high density plasma, light cannot travel freely. And so that's why the universe is opaque. Because what happens is that light will suffer electron scattering. So the electrons are moving relativistically or close to the speed of light. And any radiation that's in the situation will just be interacting with electrons continuously and not able to travel freely. So this is an opaque situation, sort of like being in the inside of a cloud where light interacts with tiny water droplets all the time and continuously, and so you can't see through the cloud or into the cloud from outside. What happens as the temperature drops through about 3,000 Kelvin is that 2 things happen this is in an expanding universe framework. 2 things happen that are physically related but not the same. One is called recombination, and that's when the temperature drops low enough, electrons can now be bound to nuclei, and so you can have stable atoms forming for the first time. And the stable atoms, of course, take electrons out of circulation as things that will scatter radiation. And so the universe also becomes transparent. So these 2 physical things happen at the same time, and it happens about 400,000 years after the Big Bang, when the temperature is about 3,000 Kelvin. And it doesn't happen instantly, so there is a time interval over which it happens, and it's roughly 30 or 40,000 years, all occurring 400,000 years after the Big Bang. So it's not instant, but it's a fairly short interval of time in this very young universe.
Excellent. Thank you very much. The next question is from Pablo, who's on with us live, who would like to know, can fossils be found on Mars?
That's a great question, because we'd love to be able to search for fossils on Mars. people are not sure if Mars could have existing life, that life could exist on Mars now. It can't really exist on the surface because the surface is very cold and has very low density atmosphere, and so is blasted by cosmic rays and ultraviolet radiation. So it's probably sterilized. The top centimeter of the Martian soil is probably sterilized. It's entirely possible that there are subsurface aquifers where the conditions are suitable for microbes. So there could be living life under the Martian surface, but probably so far down that no rover that we're planning or mission that we're planning in the near term will be able to find it. So the best hope for showing that Mars has had life, or that life could even exist beyond the Earth, is for looking for ancient forms of life on Mars, because we believe Mars was warmer and wetter and had shallow seas 3 billion years ago, maybe 2 billion years ago, before it dried out and lost its atmosphere and got very cold. So yes, looking for Martian microbial fossils is a very important experiment to do, and that's pretty much exactly what the future wave of Mars missions, especially if we send humans to Mars, geologists and biologists to do real experiments, will try to be looking for these microbes. But there is a problem, because these very simplest forms of microbial life, which are essentially prokaryotic forms of life, the earliest forms of life on the Earth were cells with no nuclei. They're very small, and they may not exist in colonies of bacteria. So looking for individual microbial fossils of that scale is very difficult to do. The morphology, or the shape or the structure in a rock, which will have crystals and grains and all sorts of inclusions and complex structure, is very hard to do. On the Earth, the way we show that microbes existed 3.5 to 3.8 billion years ago is by looking for tiny isotopic imbalances between normal and radioactive carbon, if we imagine that life metabolized carbon. And that isotopic imbalance of carbon in rocks on Earth is an indicator that life existed in that rock. And we'll use similar methods on Mars. But it's not really what paleontologists would call a body fossil. That is, the fossil of something like a trilobite or an ammonite or something, some familiar macroscopic fossil. We don't expect to see those kind of creatures just in the soil on Mars. We're going to be looking for microbes, and the fossils of microbes are extremely subtle and hard to show that they exist.
Excellent, thank you. The next question is from Horatio, who sent an email question. What is quantum computing? How is it different from digital computation? And how is it useful for astronomy?
So quantum computing is, a current wave of computation which could increase the power of computers, which have been gaining power by Moore's law for almost half a century now. Could increase them even more dramatically, or continue Moore's law's progression of computation speed per unit price into the foreseeable future. In a normal computer, the information is held in bits. Bit is a contraction of binary digit, and it essentially is using gates and switches and digital electronics in a silicon substrate to hold two states, a 1 or a 0, on or off. And so that's how a binary digit comes about in silicon, and we can miniaturize these processes and so have a very high density of information storage and manipulation in a silicon substrate. But it's binary. It's either a 1 or a 0. There's no intermediate state. In a quantum computer, we actually have intermediate states, because what the state fundamentally is not a bit, but it's a qubit, where that's a contraction of quantum bit. And a qubit is an entangled state of matter. It's actually two atomic states that are quantum entangled or coupled, such that if you change one part of the entangled state, it has an impact on the other part of the entangled state. And so that creates a probabilistic version of a bit, where the probability can vary between 0 and 1 in an arbitrary way, depending on how you entangle the quantum states. And so this is a very subtle way to hold information. And what it actually allows you to do in practical terms is parallelize calculations which in a regular conventional computer you'd have to do serially. So the way computers gain power is by the speed of their switching of these digital states and just by the density of these digital states. A quantum computer can also use miniaturization because you're talking about individual atoms and their quantum states, but because it can hold probabilities instead of a 1 or a 0, it increases the information density, if you like, enormously and allows you to parallelize a computation at right in the individual elements of the computer as opposed to by programming. So it's very powerful, and that is what gives you enormous speed gains computationally. Now, constructing a quantum computer is difficult, so we can create entangled quantum states, but I think as we speak, the most sophisticated quantum computer prototype only involves maybe 100 or 150 entangled quantum states, and it does indeed demonstrate these spectacular speed gains, but it's still a very small number of qubits compared to the number of bits in a conventional computer. So we're going to have to scale up this technology, this digital quantum technology, by orders of magnitude before you have a computer that will rival the most powerful conventional computers that we have. However, it's a huge market. It's a big research agenda. Tens of billions of dollars a year are being spent by various companies and government research labs on scaling out quantum computing, making it a reliable, powerful thing. So it'll happen. I think it'll be another 10 or 15 years before quantum computing hits the mainstream, however.
Thank you very much. The next question is from Dax, who is on with us live. I consider that the so-called black holes are the beginning of galaxy creation. Is this a correct way to understand the formation of galaxies? What's the process like?
It's an open research question, a very interesting one, of which came first, black holes or galaxies. It's a relevant question because every galaxy we've inspected so far in the local universe has a black hole at its center, and the black holes typically scale with the mass of the old stars in the galaxy. So giant elliptical galaxies, which are almost all old stars and very massive, have huge black holes, billions of solar masses. A galaxy like the Milky Way has black holes that are maybe millions or tens of millions of solar masses, and so on. So we have this interesting scaling between galaxies and their central black holes. Remember, the central black holes are still a small fraction of their total mass, like 0.1%. But that correlation does suggest that somehow they formed in concert. Now we know in a more distant, in sort of the later evolution of the universe, that galaxies have grown by mergers. And so when a galaxy with a small black hole, a small galaxy with a small black hole merges with another similar object, the galaxies combine their stars and the black holes combine their masses. So the two things grow together. The question arises, though, how did this start? Did the first generation of very small galaxies just nucleate black holes by collapse of gas and stars in the central regions naturally? Or was there a set of seed black holes around which galaxies nucleated? So chicken and egg type question. It's a very important question. It may seem like a subtle distinction. And the answer is we don't know, because this early process of the first black holes and the first galaxies happened about 100 million years after the Big Bang, 50 to 100 million years after the Big Bang. We can't probe this era yet. That's one of the things James Webb Space Telescope was built for. The theory, in advance of observations to define what actually happened, the theory suggests that the black holes may have come first, because we anticipate in the early universe, when the first large gas clouds collapsed, they probably formed an early generation of stars called population 3 stars, stars that didn't have any heavy elements because none had been created yet. And in that situation of no heavy elements, the stars that form can be quite massive, up to 100, 200, 300 times the mass of the sun. And those stars will leave behind fairly beefy black holes of 50 and 100 times the mass of the sun. And those would make good nuclei for the formation of the first generation of galaxies. So theory suggests that the miniature seed black holes formed first, galaxies formed around them, and then they grew in concert. But we don't actually know the answer yet.
All right, the next question is from Surjith, who sent an email. Do black holes have a temperature? If it isn't emitting anything, wouldn't this make its temperature absolute zero?
Until Stephen Hawking did his work in the 1970s, yes, black holes were presumed to be absolutely dark because nothing can get out, no radiation, no matter, and a dark object indeed would have a temperature of absolute zero. So Hawking's contribution, one of his many contributions to black holes, but perhaps the most famous one, was the idea of Hawking radiation. He looked at the region around the event horizon and showed that there was a chance that virtual antiparticle and particle pairs that happen all the time spontaneously from the vacuum and then disappear again. We see this happening in the lab, so we know it's a real physical effect. This process played out near the event horizon leads to a finite chance that either a particle or an antiparticle will escape. And the net result of that is either radiation or equivalently mass escapes the black hole at a very slow rate. And so black holes both radiate and evaporate. So Hawking radiation has these twin implications. And when you work out the level of Hawking radiation, calculations that Hawking did, of course, for the first time, and others have repeated since then, you deduce that the Hawking temperature, the Hawking radiation temperature of a black hole, the mass of the sun, is a billionth or a few billionths of a Kelvin. So it's not absolute zero, but it's a very, very low temperature, which also implies that the rate of Hawking radiation or the rate of evaporation is very slow. And so this is unobservable, both the evaporation process and the radiation that results from evaporation. These are unobservable and may always be unobservable. A billionth of a Kelvin is an impossible temperature for real astronomers to measure. So while we think black holes are not entirely black, we haven't shown that that's the case yet. Hawking was disappointed by this. He died without Hawking radiation being detected. And that was a disappointment because Nobel Prizes are awarded for discoveries, not for theories. And that was really Hawking's best shot at a Nobel Prize if Hawking radiation had been discovered in his lifetime, but it wasn't.
All right, the next question, I think we've gotten this from a couple of people, is from someone who's on live. Surya sent an email as well. Can you talk about what kinds of opportunities there are for jobs in astronomy, and what are the chances of someone getting a job in astronomy? But then I thought maybe you could talk about sort of related careers, and then what do people do if they get degrees but don't make it in, find a faculty job in astronomy? What are some other opportunities?
Right. So there are a range of jobs in astronomy and associated with astronomy. The pure, the sort of classical jobs in astronomy are to be a professor or an academic in an astronomy department where you teach astronomy and do research in astronomy. But many astronomers work in research institutes, and so they don't teach, but they do research in astronomy. So there are a set of astronomy jobs that are purely research and not teaching. And because astronomy is a field that depends on technology, the technology of instruments and telescopes, a lot of jobs in astronomy are sort of technological jobs. There are people who are instrument builders, and they are often employed by astronomy departments, and their colleagues really consider them astronomers who have experimental expertise. And so there's another set of people with technical or computational expertise who are working in astronomy departments, doing astronomy from a perspective of experimental physics or computational science. So those are related jobs. There's, of course, another set of jobs in astronomy, broadly described, which involve the support work associated with astronomy. Some of these are, again, technical jobs. They could be jobs like telescope operators, people who work with the astronomers at the telescope and safeguard the equipment and make the telescope function. So there are a range of jobs, and there are even a small number of jobs that are associated with policy and with creating the enterprise of astronomy at an institutional level. So that creates quite a significant spectrum of jobs. The academic jobs in astronomy are actually a small fraction of all the jobs in astronomy, but it's a niche discipline. So relative to physics, is probably about an order of magnitude smaller workforce than physics.
Excellent. Thank you very much. This is going to be I guess we probably have time for two more questions. So The next question is from one of our live viewers. Sorry, I lost my place in here. Does dark matter interact with space-time the same as regular matter? Does it bend space-time like regular matter?
Yes, that's a good question, and absolutely it does, because the relativity, the premise in general relativity is that mass and energy curve space and time. So mass energy is hyphenated because those two are related by equals mc squared, and space and time are related through the equations of general relativity. So since dark matter clearly has mass, it absolutely does bend space-time. And when we look at the situations of gravitational lensing, these are images that Hubble Space Telescope's taken dozens or hundreds of these images in its 30 years in orbit. Most of the bending of the light of distant galaxies by an intervening cluster of galaxies or an intervening galaxy is caused by the dark matter, because the dark matter is 6 times more than the normal matter. So in fact, most of the bending of space-time and the curvature of light traveling through that space-time is actually caused by dark matter. And inverting that logic, it's those lensing experiments that allow us to weigh galaxies, that allow us to weigh dark matter and say that it's 6 times more abundant than normal matter.
All right, the next question, and this will be our final question for today, is from Nilesh, who's interested in about the SKA, the Square Kilometer Array. What's the current status, and what is it going to be looking at and discovering for astronomy?
So the Square Kilometer Array is the sort of frontier radio facility in worldwide astronomy. In simple terms, the Square Kilometer Array will improve the sensitivity of the best radio telescope array by a factor of 2 orders of magnitude, so by a factor of 100 relative to something like the Very Large Array in New Mexico, a familiar facility that we've had for a couple of decades. The Square Kilometer Array is being built in Australia and South Africa, and it's not one single set of telescopes, it's a range of telescopes. There are sort of mesh telescopes or even wire array dipole type telescopes in a central region, and then there are a larger, more distributed set of antennae or dishes, radio dishes, working at centimeter and millimeter wavelengths, and spanning a continental size dimension within 4 countries in Africa, spanning 4 different countries in the southern part of Africa and pretty much the entire continent of Australia. And the spacings of thousands of kilometers or tens of thousands of kilometers between the different telescopes are what gives the Square Kilometer Array its resolution, its sharpness of imaging radio waves, and just the sheer number of dishes, I think total of 10,000 dishes, small and large, is what gives it its incredible sensitivity. So it's an amazing project. It's a multi-billion-dollar project. It's the largest science capital project Africa has ever been awarded. So it's an incredibly important facility for African science and African astronomy. Never anything of this scale has been done in that whole continent. And at the moment, it's in its test phase. So there are test versions of all the major antennae. And I've been to South Africa within the last 2 years and visited one of the test facilities in the sort of the belt, the Savannah country north of Cape Town. And it will fully come online probably just slowly and steadily over the next decade. So probably in about 7 or 8 years, it'll be at close to its design sensitivity. And it's going to transform radio astronomy, because anytime you get a gain of 2 orders of magnitude in sensitivity in any wavelength regime, you find new things, you make discoveries, you sort of transform your understanding of the universe for that type of radiation. So it's a very impressive facility. So thanks for all your questions, and thanks to Matthew and Alexander for facilitating this session, and we'll be back with you next week.